Hello and welcome to the Titus Timeout podcast. I'm Jenny Abney-Civey, and this week I want to follow up on last week's podcast on Bernoulli's principle by discussing duct pressure losses. So last week I discussed how, as air flows through ductwork, you can change the static and velocity pressure by changing the size of the ductwork. I assumed that the total pressure stayed the same in my little small examples, but in reality, the total pressure decreases as it goes through the ductwork due to friction and some other things. So I want to start with this drawing from ASHRAE Fundamentals. So let's say that you have some ductwork that pulls air from outside, and then drawing these transitions, put in the rest of the ductwork. So now that you can see, you have airflow coming in here, we'll have a fan in the middle, and we'll have air discharging out this end. Okay, so let's look at the pressure profile of this little piece of ductwork. I'll draw a line down here, and that's going to be atmosphere. So the air being pulled into the return, and the space that's being supplied is just at atmospheric pressure. And now let's draw some lines down to show each of the transitions. So each place that something's going to happen with the pressure will have this little purple line. So now let's look at the total pressure as the airflow goes through the ductwork. So we're starting at atmosphere because you're pulling from outside the space. So you'll start about here at the inlet of the system. It's going to come in, I added a little bell mouth, so it'll come in there. There'll be a little bit of pressure loss. Then it'll go down the duct. There's a transition, so there'll be more total pressure loss, a little more straight duct, transition, so a little more total pressure loss. Then it gets to the fan, and the fan boosts the pressure up here to above atmospheric pressure. Finishes the ductwork. Again, there's a little bit of loss, a loss at the transition, a little more straight duct. It hits this pretty hard expansion. There's more pressure loss, goes out, and then it hits the space and will return to atmospheric pressure somewhere after the end of, we'll say, the diffuser, which I didn't draw in. So now let's go back and do the static pressure as well. So the static pressure goes down with the total pressure. We have a transition here. We lose total pressure, we lose static pressure. A little more straight duct. Now here you get an expansion, so the velocity slows down, the static pressure will go up along the ductwork, gets a boost through the fan, following along the ductwork again here. Now the velocity increases, so the static pressure will be reduced. Then follows the ductwork, and now we have an abrupt change. The velocity decreases, the static pressure will increase, follows the ductwork, and then out into the space. Okay, so let me label these. The green line is static pressure. The blue line on top is the total pressure line. And the difference between these two lines is the velocity pressure. So like in this spot, the velocity goes down because the ductwork gets bigger, the velocity pressure goes down, and the static pressure increases. Okay, so let me make a little space. So today I drew that the total pressure went down in these little sections of straight duct. That's because there's some loss in the ducts due to friction of the ductwork. The type of ductwork, size, shape all affect pressure differently. The rougher the ductwork is, the more friction loss it'll have. So unlined ductwork will be less rough and therefore have a lower friction loss than fiberglass lined ductwork or flex duct. As far as the shape of the duct goes, round ductwork will have less pressure loss than rectangular ductwork because there's less surface area. So if you look at this round duct and say it's 12 inches and this is 9 by 12 inch rectangular duct, the area of this 12-inch round duct is pi r squared is about 113 square inches. The circumference of this is 2 pi r, and that comes out to be about 37.7 inches. Now if you look at the rectangular ductwork, the area is 9 times 12, which is 108 square inches, and the perimeter, which I guess I should have labeled P, is 9 plus 9 plus 12 plus 12 is 42 inches. So you can see that there's a little less area in the 9x12 duct, but it has more surface area to interact with the air. So the closer to round or even square you can get, the lower the loss. Inlet and outlet transitions will affect pressure loss as well. The more gradual the transition, the lower pressure loss. So a bell mouth is probably the best, and then a slight angle down to the smaller ductwork. And then the worst is going to be just a hard transition from one to the other, and that'll have the highest loss. Bends in the ductwork will affect pressure drop as well. The harder the bend, the higher the pressure loss. That's why you often see turning vanes in 90-degree bends. They guide the airflow around the corner, reduce the turbulence, which reduces the pressure loss. These pressure losses fall into two categories: frictional losses caused by air moving through the ductwork, and dynamic losses caused by disturbances of the airflow from changes in direction or area. So these top ones would be friction losses, and the bottom ones would be dynamic losses. So that's the basics of duct pressure losses. Don't forget to subscribe to our YouTube channel, and thanks for taking the time out with us.